Dr. V.V. Kamesh, Professor of Mechanical Engineering, Aditya Engineering College. Now, how to construct the velocity diagram for a 4-bar mechanism? Because the 4-bar mechanism is the fundamental entity of the kinematics of machinery. So, we are having the 4 links. The first link is link 1 and this is link 2 and this is the link 3 and this will be the link 4. For the general considerations, we are fixing the ground link AD and this smallest link, whatever we have out of all these other 3, we will give the rotation in the clockwise direction or anti-clockwise direction. This element we are calling with the name crank. As usual, this link BC is called coupler and this link 4 where we are getting the actual output measurement, it is called rocker. These are all the general things of the introduction for the 4-bar mechanism. Now we need to identify what are the velocity of different points on the 4-bar mechanism. Initial case only A, B, C, D, only these 4 points are being considered. After that we will consider the intermediate point E and offset point F. So, in this case whether it is a 4-bar mechanism or it is an extended version of the 4-bar like 5-bar, 6-bar, 7-bar, anything with the different compositions and different physical parameters with the slider or with the rotation or revolute joints, any type of joints. Initially we are considering the revolute joints here A, B, C, D, all the 4 are revolute joints. This mechanism for the basic one 4R mechanism. So, in this 4R mechanism, to get your velocities of B, C, D, E, F or any other thing, initially we need to identify where is the input. Where is the input? The input is with crank rotation. Always the velocity diagram has to be started with where is the input. Answer to this question as it is crank rotation. Then where is the crank? What is the crank? Crank is AB. That means crank is rotating. When crank is rotating, it is giving one data. Either it is the N in the RPM or the same thing with the omega in radians per second. That means when crank is rotating with some 120 RPM or crank is rotating with radians per second. So, this data will be given to us. So, once the crank rotation is given and the crank length is given, when angular velocity is given and the length is given, then we are able to identify the velocity of crank. That means velocity of the crank means velocity of any point on the crank. It can be known to us. That means initially we will be supplied the lengths AD, AB, BC and CD. AD may be some 120 mm. Let us take some arbitrary numbers here to represent. AB some 25 mm and BC some 72 mm and CD some 66 mm. Like this, the length parameters will be given to us initially. So, from these length parameters, we will construct first ABCD. After constructing the ABCD with the geometrical construction procedure, then N RPM or omega radians per second will be given to us as an input. Now, how the velocities of different points B, C, D are A, because the A is fixed one and D is fixed one. Velocity of A will be 0 and velocity of D will be 0, right? As many elements, those who are having the 0, all are taken as single point in the velocity diagram. That means A and D. So, initially we will take A comma D to represent single point in the velocity or configuration diagram. Now, see, in the 4-bar mechanism or any mechanism, always we remember a single point, fundamental point. Velocity is always perpendicular to link. Velocity of any point, so extending velocity of any point on link AB, or otherwise we will write link PQ, maybe a generalized case. Velocity of any point on the link PQ will be perpendicular to the link PQ. So, already we are being supplied the length parameters in the diagram itself. So, where will be the velocities? Always perpendicular to these links. So, very easy, but the direction will be primarily important. Secondarily, we will get all the directions automatically in the velocity diagram. Now, this is being rotating in the clockwise direction. That means like this. So, it is rotating in the clockwise direction. Then how the velocity will be? In this direction. When this is, the link is like this, the velocity will be perpendicular to the link. That means in this direction, right? Now, velocity of B with respect to the A will always be perpendicular like this. That means V, B, A, right? Now, suppose we are extending the discussion to C. Velocity of C with respect to the B, how it will be? Perpendicular to link BC. So, to this perpendicular, let us take like this, velocity of C with respect to B, because it is very clear that it is rotating to the clockwise direction, we can take this one in this direction, or it may be in this direction. So, once we are having a point and secondary point, velocity of C with respect to the B can be in this direction or in this direction. So, after that we are having a shortcut procedure or a simple rule how to identify the velocity of C with respect to B or O, whether it will be left direction or the right direction, right. In the 4-bar mechanism, it is very easy to identify. In other mechanisms, we need to identify with some calculation part. So, here, so this is velocity of C with respect to B will be perpendicular to the link BC length parameter. Now, how to identify the velocity of C with respect to the D? Then, velocity of C with respect to D has to be perpendicular to link length CD. That means, take a line perpendicular to this, perpendicular to this. So, velocity of C with respect to D or velocity of C with respect to the D. So, you can take the two directions, anything may be possible, right. Here also velocity of C with respect to the B may be in this direction or in this direction. In which direction it is taken, that will be dependent on in which direction the angular velocity will be for that particular link, it will be transferred to the link itself. So, when omega is like this, velocity will be like this. When omega is like this, velocity will be like this. This is the omega, this is velocity. Because once it is rotating like this, the velocity has to be in this direction. If it is rotating in this direction, the velocity will be in this direction. Like this, First we need to identify where the omega direction will be according to the crank position. If crank is rotating in this direction, how it will be transferred to rotation of the links BC and CD. So we will see there is a very easy procedure how to identify the this is A, this is B, this is C and this is D. Suppose I am rotating this element like this element like this. So the new position, then this will become B2, B1. Then once it is being extended like this will be moved like this. C dash or C1, whatever it might be. Then so this is the new position of B1, this is the new position of C1. So even though the total link is rotating like this, but the C with respect to B, C and C1 and B and B1, this is rotating in reverse direction. That's why the easy one is the relative velocity of B with respect to the A can be known with the velocity component, but the direction of angular velocity, it is simply alternately clockwise, anti-clockwise. So crank is rotating clockwise. That means this will be rotating anti-clockwise. Again this will be rotating clockwise, right? So from C, this is very small angular displacement. This is very bigger angular displacement. So the angular displacement itself will be saying this is rotating in anti-clockwise direction. So shortcut means actually what is happening in the 4-bar link mechanism. The omega AB or BA, whatever it might be, direction will be like this, and omega BC or CB, whatever it might be, it will be like this, and omega CD will be like this. That means it is moving like this. Once you are making moving like this, automatically this will be lifted up like this. That's why omega BA direction will be here, this direction will be like this, and this direction will be like this. After identifying the omega AB, omega CB and omega CD, now the first thing we need to identify calculation of velocity AB. So from the given parameters of the length parameters AB, VAB can be easily calculated by omega AB as a input by length AB. Then we will get some value with respect to some given parameters. Suppose omega AB is 20, the length is some 40 mm or something, 40 mm into 1000. So this will be 500 meter per second. With this 500 meter per second, now I need to identify this is VBA. So starting with standard points or fixed points of the link A comma D. So take A comma D. In the direction of VBA, we need to draw a line AB such that the line AB will be equal to 500 meter per second. That means velocity of B with respect to A, VBA, or we can write with the capitals VBA like this, or VAB. So this is the line 500 meters per second we are representing with the calculation VAB. After that, now velocity of C with respect to B or velocity of C with respect to D. How these will be calculated? Now, if we identify point C, already point A, D are fixed one. We identified point B by means of the input parameter. If we identify point C, then A, B, C, D link parameters are completed. Now, how to identify C? Now, C is a common point for the two velocity profiles, velocity of C with respect to B and velocity of C with respect to D. Now, C is a common to both. Now, if you draw the velocity lines of VCB and VCD, they will intersect at the point C. Now, how to get the velocity of CB? That means it has to be from BC line. I need to get BC line on velocity diagram. Next, velocity CD, I need to get DC line. So, from our calculation, already some parameters are available to us. So, initially we are making A comma D. Parallel to this, we are making B. This is the velocity B with respect to the A. Now, perpendicular to this BC. That means initially I want to find the line BC. So, B is available to me. Now, I need to get BC. Where will be the BC? Always perpendicular to the link BC. So, perpendicular to the BC in the direction, we need to make a line perpendicular to this from B. I need to draw a line to the top and bottom. So, somewhere C will be there. That means this is the locus of C. So, I am searching for point C somewhere here. It may be here, it may be here. So, there is no exact calculation of the precise one. It can be in the upper direction or the lower direction. We need to draw a bigger line, right. So, this is the locus of C. On this, C will be there. Now, I want to get DC. DC line will always be perpendicular to the link CD. So, where is CD? This is CD. So, perpendicular to this, I need to draw another line perpendicular to the link parameter CD. So, drawing a perpendicular line, this is the CD extended line. So, perpendicular to this, I need to draw a line. This line is called again locus of C. Here also to the left extension I can make as a procedure. We are making to the left and right here locus of C. This is also locus of C. So, as usual, this intersection will be satisfied C point. That means AD are the fixed points, B is identified from the input data. Now, from the link perpendicular lines, BC perpendicular, this BC and CD perpendicular, a line from D, they will intersect and C will be identified. So, this will become velocity of C with respect to D, this will become velocity of C with respect to B. As a vector notation, we can write very easily velocity of CD or CA, whatever it might be. Velocity of C with respect to D or velocity of C with respect to A, both are same because AD belongs to link. Okay. How to write the velocity equation of VCD? Velocity of CD is equal to, this is in this direction, and what are the continuous vectors? VBA and VCB. So, this is equal to VBA plus V CB. That means in the diagram DC is equal to AB plus BC. Okay. Otherwise, if somebody is reversing the item like this is equal to VBC. Suppose instead of writing VCB like this, if we write VBC, what will happen? This is the single vector and these are the two continuous vectors. Now, this VBA can be expressed as a summation of the vectors VCD plus VBC. That means AB is equal to DC plus DB or AC plus CB. So, AB is equal to AC plus CB. Like this we can represent in a vector notation. But whatever the direction we are having in the reversal, it is only for the representation in the vector notation like this. It doesn't make any sense in our numerical calculation because AB is representing 500 meters per second. Whether we are representing to the upward direction or the bottom direction, whatever it might be, the numerical length BC, it will not change. So, from your scaling of whatever scaling we are taking here, take the scaling BC. That means velocity of C with respect to B or B with respect to C. Both will be having same magnitude, but the representation will be in the reverse direction. So, similarly, AC, this length will be identified with the same scaling. We can calculate velocity of C with respect to D or the reversal velocity of D with respect to C. But practically speaking, we should not say anything about the velocity of the fixed point with reference to other point. It is ridiculous because A and D are fixed points. So, even for the calculation part or text matter, velocity of A and D, they are 0. With reference to any other point, if it is a reverse in this direction, we need to cancel this. Always the velocity of the moving points C or B or next we are having some E and F, they are to be known from the velocity diagram. So, the fixed point need not be directed. Here, velocity of B with respect to the A only to be considered and only to be analyzed. Reverse direction, velocity of A with respect to B, A with respect to C. So, they should not be analyzed because it is always 0. Okay. Now, how to get velocity of an intermediate point E? So, this intermediate point is on the link BC. It is on the link BC. So, on this BC, we need to identify the point E. Same proportion, we need to identify the point E on BC such that, what is the equation? Original parameters BE by BC should be equal to B small e by BC. That means BE by BC. This is BE by BC. Like this, if you are having the calculated parameters, from that we need to calculate because already BC is identified and it is calculated. So, BC is calculated and this BC is given and this BE is given. So, this small BE can be calculated directly and proportionately we can put the point E like this. Now, after identification of the E, it can be joined with the fixed point, then VEO, EA, velocity of E with respect to A can be known, or you can call velocity of E with respect to D, both are same. Velocity of E with respect to A or D can be known. Otherwise, this small portion BE, this small portion. This can be represented as velocity of E with respect to B. This small portion, velocity of E with respect to C. Like this, the same length parameter can be spread up into two proportionate elements with respect to E. Velocity of EC, velocity of EB, both will be combined as velocity of C with respect to B. Now, if any offset point is there, just like in the earlier case we discussed, the offset point lengths, again the same thing, this BF, it is taken as one link, and identification of the F, that means VFB, direction can be known, that means I need to draw line BF, and velocity of F with respect to the C, this, consider this is another link, and I need to get CF line. So, BF line and CF line will supply the point F on the velocity diagram. So, the line BF, where it will come? From B. How it will come? Perpendicular to the link BF. So, perpendicular to this. So, this line and this, they will be perpendicular. So, this is a line, BF line. So, this is the locus of, as usual, this is the locus of F. So, I do not know the F is here. So, F may be on this line. Again, I need to get CF. From where I will get the CF? Perpendicular to this link parameter. So, perpendicular to this, I need to get some CF, locus line like this. This is the locus of C. This locus and this locus, they will meet together to get point F. So, after identification of the F, so it can be joined with the original fixed point AD, then we can represent this is VFA, or we can call VFD. And if the direction is like this is representing VFB, this is representing VFC. If the direction is reversed, we can call VCF. So, like this, from this identification, this procedure, we are able to identify and calculate the velocities of different points A, B, C, D, an intermediate point E, and any other offset point F.